the table. Yeah, so we have, how does a traditional computers differ from a high performance computing systems? So generally speaking, again, this is not every illustration that I'm making. It's not like Bhagavad Gita or, it's cast in stone. It's just an illustration. So there are today systems which has got so many processors. Some of them are using it at their homes. But generally speaking, traditional computing will have minimal processors, single or a few processors. HPC, so many processors that we are talking about. From a speed perspective, it's limited by that whatever number of processor it has. So it's not that fast as compared to the speed of HPC system, and ability to handle data is in smaller gigabytes from a traditional computing, whereas high performance computing goes into petabytes. And these days we have exabytes of performance that's possible. General purpose tasks today, if you wanted to solve something locally on your system, you can use your research lab systems or your own home laptop or MacBooks. So that's what your traditional computing does, and high performance computing largely is used for solving scientific and engineering problems. So with that in our memory, let's again one more time just wanted to establish the baseline for all of us clear. So HPC, from a definition, clusters, powerful processors, parallel ability to solve massive multidimensional data sets at very high speeds. So we spoke about speeds. So when we say speed, what are we talking about? We are talking about the ability of a system to process flops, is what we call FLOPS, billions and in fact exabytes of floating point operations in 1 second. And the general uses for HPC systems are, as we saw in the previous slide, scientific research, engineering, genomics. And if you ask me from a financial side, where are we using HPC? There is a notion which we will kind of touch upon towards the end. There is something called high frequency trades, HFTs is what we call in the finance side. Now what happens, everybody puts in a trade and it takes some time to process, but imagine millions of trade processed in nanoseconds. So that's what is high frequency trading is all about. And what happens in those typical HFTs, high frequency trading solutions, is that there could be frauds. Buy, BUY I'm referring to, and then sell, buy, sell, buy, sell, buy, sell. And imagine all of that, millions of transactions happening in nanoseconds. How do we eliminate frauds? How do we detect the pattern of a fraud there? Regular systems, servers that we typically use cannot solve that. So to process frauds at real time, that's where HFTs, specifically in the sphere of high frequency trading, we use HPC. When I say we, financial companies, financial sector typically use HPCs. So with that, I just wanted to, at a very high level, touch upon the use cases, but somewhere down we do have use cases in a little bit of more detail. So what do they use? Monitoring weather systems. We keep hearing about hurricanes and storms all over the globe. So it helps in tracking storms. Gene sequencing is an area where HPC is phenomenally used. And autonomous vehicles, needless to say, in terms of figuring out at real time, lots of data that an autonomous vehicle sort of creates. How do we process all that information? That's also another area where we use HPCs. Okay, I wanted you to all reflect upon this image that you see on the screen. This is just to give an analogy of someone who is a librarian. His job here is to read every page of every book in the library, compare that with every other book, read every other book, every page of that, and just check if there are any patterns that are that could be created, that is available. Is there any correlation? And we are talking about 1 billion books in this huge library, and this is just not one library. If we are really imagining, we are talking about millions of libraries. Imagine the complexity of this task. Now, if you replace the word books with DNA, how many people that we have, how much of information that need to be processed, it's unbelievable levels of complexity, isn't it? To figure out from one genome to another genome, what's the level of complexity? What's the sort of a patterns? What's the correlation that we have? It's not easy at all. So those are the sort of complex problems that high performance computing typically solves. So that's what I would want to have you all think about it. See, I've put this presentation in a way that, because it's starting off with foundations, very easy to understand, hopefully, as we progress along. Now, we spoke about HPC, we understood the definition, we had all those P's of HPC that we spoke about. Now, what are the key features typically in a high performance computing? We had the P about parallelism. Now, parallelism, as we already said, a big task broken down into multiple smaller parts. That's very easy for all of us to understand. But what if I say it's just not tasks that are broken down, it's also the data that gets broken down. So typically you would have task parallelism, where a big task is broken down into smaller parts, and these are pushed to the processors, and all of these individual processes analyze that, and then there is a combination that happens towards the end. So that's task parallelism. What's the second type? That's data parallelism. Now, we spoke about the genome example in the previous slide. Huge amounts of data. The whole idea is to detect a pattern. You can't, despite the power of any processor, you can't have all the data to be sent to one single processor, right? So you will have to split the data into multiple smaller chunks. Now that's where the element of data parallelism comes in. So parallelism has two aspects: task parallelism and data parallelism. Now the second key feature of HPC is about scalability. Now, the very concept of scalability, if many of you are from the field of computer science, you would know there is a notion called vertical scaling, where you start taking one system and continue to enhance its capability to process or enhance its computation. Or there is something called horizontal scaling. You continue to keep adding additional processes to it. Something similar is what is applicable in HPC in terms of scalability. There are two aspects. One is strong scalability, and there is another notion called weak scalability. Not to confuse you all, very simple example. I've got another slide to help you differentiate, but for now, you just understand that there is, if a problem is fixed and we really have to solve that problem in a lesser time, imagine that you're given a task and the task need to be handled by one person. He or she takes 8 hours. Now you need that faster. You need that in 4 hours. So you add another person. So that the entire task gets divided, right? So that's the notion of strong scalability. But let's say if I had 100 persons to finish this task, is that too many processes that need to be added? Will it really help me to solve it? There is some communication that need to happen. So those are the complexities or challenges that we generally face in a HPC architecture or a design, where it's not just about adding process will help in reducing time. There is no such direct relationship. There are some communication overheads. Just for now, understand that those need to be solved. I have nice graphics to explain that to you later. High throughput, very common knowledge about what high throughput is. If my HPC system should be designed in such a manner that it processes large volumes of data. We spoke about genomics, drug discovery. Imagine the combinations of molecules, that the interaction between the molecules that need to be assessed to really create that drug which will solve a specific epidemic or a disease. Look at the kind of combinations and the volumes of data that need to be generated out, right? So that's what is called as high throughput. So when we design an HPC system, these are the factors that one takes into consideration. We spoke about strong versus weak scaling. I gave you an example. I just wanted your attention to the bottom of the slide, if you're all able to see my mouse scrolling around, just to understand. I've attempted to keep it as easy. I basically belong to Tamil Nadu. I did my schooling, everything in Chennai, but moved to the next state, Karnataka. I've been there for a good amount of time. My work is in Maharashtra, as in Mumbai. So I keep traveling often from Bangalore to Mumbai. So just given a very simple example for all of you to understand what is strong scaling and weak scaling. So if we have to predict weather related symptoms or simulations, weather prediction for say TN, one processor, we will be able to manage this for the entire Tamil Nadu. If you put in two processors, the same job, predict the weather patterns in TN, could be solved much faster, half of the time that a processor has taken. Naturally, you increase the processor, it will get reduced by that many numbers. So 4 processors, a quarter is what the efficiency of each of the processors. So in strong scaling, the concept is efficiency of each of the processor decreases as you keep adding more process. That's all. Very, very simple concept. You add more process, my utilization of the processor comes down. So that's what it is. But what we should also be concerned when somebody designs an HPC is, can I add 100 process? No, because there is going to be a communication and coordination between this process. So if it solves one problem, I need to take that subset of the solution of processor 1 and then ensure I gather the subset that processor 2 solves, combine them together. So there's a lot of coordination and communication overload. So that's strong scaling for you. Weak scaling, very easy. It's like I have a fixed number of processor. I'm utilizing the processor capacity to the fullest. And I do it for, let's say, as an example, climate modeling for TN, and you're able to do that with one processor. But suddenly some good friend of me comes and says, hey, why not just TN? Why not you increase the scope of the workload? I would also need to do it for K. I would also need to do it for Punjab and Himachal, When we increase the workload, you then gradually increase the number of processors to handle the additional workload. So in weak scaling as a concept, efficiency is maintained by each of this process so that as you get still the opportunity to expand the workload. So that's what is weak scaling here. So far we have seen what is HPC. We have understood some of these elementary notions of features of HPC in the previous slide. We touched a little bit more deeper into strong and weak scaling of HPC. Now with that, it's obviously when we are talking about the foundations, we need to know the intrinsic of HPC. If I were to really visualize what a HPC is, what components does it have, I need to understand some of those elements, right? So that's where I would want to now introduce in the next 2 slides about very fundamental stuff around the hardware and architecture terms related to it. First is very simple node. We keep talking about, I have 10 nodes, 15 nodes. Node is nothing but a simple individual computer, and it would have CPUs, memory, GPUs. So that's what a node is. The cluster is group of nodes put together is a cluster. Now, if these nodes are acting in isolation, nothing happens, right? They need to talk, they need to connect with each other. And that's where the interconnect as another component comes in. Typical interconnects that we generally hear in the HPC world is InfiniBand and Ethernet. So how do you maintain the communication between these nodes is what is managed by interconnects. A core, overused, I would say a word in computer science generally, but what is a core? A core is simple. It's a processing unit with a CPU, and it has this ability to complete an instruction. So that's a core. GPU is a specialized, I would say, processing unit. It's built in such a manner that it has an ability to process or break down tasks or do the optimization by running multiple tasks in parallel. So that's what a GPU. Needless to say what memory and storage is. I'm not going to talk too much about that. There is a concept called accelerator in the world of HPC. Now, what are these accelerators? Some of you may have a maths background, perhaps. Matrix multiplication is too complex. Some of you may definitely agree with what I'm saying. So how do you ensure that computations can be optimized and fastened in a special way? So that's something what an accelerator in a HPC does. FPGA is a good example. It's field programmable gate arrays, I think. That's what it is, FPGAs. Sounds very fancy, but what it simply does is, if you give it a task, it does with the better usage and programming ability, you'd be able to complete a specific operation in a much optimal way, in a better optimal way. So that's what an accelerator does. Hybrid architecture, as the very name suggests, it's a combination of multiple CPUs and GPUs. Floating point flops, as I said, is floating point operations per second. How do you determine my HPC is doing good, right? So the primary measure is what is flops. Rmax and Rpeak are another measures. And as an analogy, I like giving analogies. If you're driving a car and if you're looking at your speedometer, um, the maximum speed as on the speedometer probably would say 240 kilometer per hour. Now that is something not achievable on our roads here, and specifically in Bangalore traffic. It's very much there on the dashboard. That's about it. So that element of what is the maximum theoretical peak performance is what our peak is. R max is about considering your traffic conditions and all of that in real world. Similarly, given these constraints, what is the sustained performance that could be provided by an HPC system? That's defined by R max. So R peak is 240 kilometers. R max coming from Bangalore is 10 kilometers per hour. So that was a joke. It's not that bad. The traffic is improving. So that's R max for you. Now, we said these nodes need to interconnect, need to speak to each other. And that's where the concept of MPI comes in. MPI is message passing interface. How do I make both the nodes talk to each other? So that's the notion of MPI. It's a protocol. And similarly, OpenMP is also a protocol. I would say it's largely like there are programmings associated with OpenMP. The only difference is we use MPI for distributed memory and OpenMP for shared memory. Now, I haven't even spoken about what distributed memory is and what shared memory is, and I'm introducing the concept. So just hang in there. You will get to know. Just understand that two nodes need to talk in different contexts. Somewhere MPI is used, somewhere OpenMP is used. Now, with all of this done, there should be always a manager, right? Somebody, we always say that I don't know what tasks I have to perform. I have this much capacity. So how do I distribute the load? And that's exactly where job scheduler comes in. It's basically saying how much of compute resources can be used for a bad job A, for a bad job B, bad job C. So how do I schedule the workload on the HPC systems? SLURM Slurm is a technique that is used. It's a standard job scheduler typically used in the field of HPC. Bandwidth, all of you would know what it is, ability to transfer data. Exascale computing, you'll get to know what it is when I talk about some of the top-end supercomputers that we have across the globe. We spoke about floating point operations, 10 power 18 floating point operations. It's unimaginable and very high. So that's the exascale computing that we have. Somewhere we are talking about RAM. Somewhere we need to write information, right? There is going to be an input-output operations. And that's where the notion of parallel file system comes in. How do I write to a location which can be accessed by multiple processes? Lustre is a very good parallel file system. So this is something which is commonly used in the HPC ecosystem. Checkpointing. If how many of you are AI ML experts, I do not know. But if you understand, I keep training the model, and at some stage I stop when I find my optimal usage. The loss is very low, and you end up stopping it, right? And you don't go back and again train the model. So somewhere we do that. So that's something similar concept extended to checkpointing here. It's a mechanism to stop your HPC job so that in case of failure happens, you can pick up that location and restart your training. So that's the foundations so far around HPC terms that we have. I believe we are doing good on time. Great. Let's move on. Not too much to gather from this because I'm sure you would by now know what it is a traditional computer does and what HPC does. Very simple, single serial computing, the older days where every task is broken down into multiple smaller instruction sets, and your processor picks up the instruction set 1. I've done it. Then it picks up instruction set 2. It happens in a very serial manner. Very simple explanation, isn't it? Parallel computing, we already spoken about parts, P1, P2, breaking it down into multiple things. So that's the notion of parallel computing. So when we generally speak about HPC, remember that it's largely about parallel computing. Let's move to the next slide. Just give you that illustration. What I just spoke about, a problem on the left-hand side, you have a problem. It's broken down into multiple instructions. One by one is what your processor picks up. If, as an example here, this is picked up from this tutorial, very good, very nicely explained. So if you want to do a payroll, if you see from T1, T2, T3, And I believe every employee, first, what does a solution starts off with? It first looks for the hours of the employee one, what is the rate card for that employee one, and then it does some calculation and then adds the tax and finishes off. So one employee's entire operation gets done, then the second one gets picked up. So that's the sort of a serial computing is. Parallel computing, very evident from the slides. I think I need not explain. Very easily problems are broken down, and each employee is being assigned to be completed in one processor. So if you see do payroll one, employee one goes to first process, second process. So programmatically, this can be managed. So that's what parallel computing is all about. Same thing said based upon the time being consumed. When you talk about serial computing, P1 plus P2, P3 is the total time that it takes to complete a task. Because all of this are done in parallel, your computing time completely shrinks, as you see in this illustration here, where my mouse is following here, right? So that's what is the total time is reduced. Now, I always like visualization because it's very easy. The picture speaks better than 1,000 words, right? That's what we keep hearing. And the more we see in terms of an illustration of this nature, it really helps in understanding the basics better. With that in mind, as you see on the slide, a simple node has got multiple processors. Each processor has multiple cores. And there is a memory which is used by these processors. There is a GPU which is built of 1,000 of GPU cores. There is a network controller to manage the communication. Power management is another element of a node, and a local storage where for input-output operations, for processing a task, they write into. Now, this entire box, if I have to put it into these smaller boxes that you see here, these are what adding up together form a huge cluster. So that's the sort of a relationship, and these big clusters form the foundations of a high-performance computing system. Now, nothing goes away without proper illustration in terms of what it is when somebody sees how does a chip look, what actually goes into the chip. That's why I just brought this slide for everybody to understand. So if you see here, this is an IBM BG compute chip. Interesting numbers to illustrate what these are. We'll get to understand each of them. So just note down these, or if you just have a few seconds to pause and figure out, there is some illustration like PUs, okay? There is something called L2s. There is something in the center which says X bar switch. Then there is a very interesting Greek word. I don't know. Maybe it's called a SerDes. What does the SerDes do sitting in a chip? So if anybody hasn't seen a chip, this is generally, and as I said, don't take me for granted. This is how a general chip looks like. There could be many variations of it, but I found this to be a useful information for all of us to understand. Now we'll get into the details of what are each of these components in the next slide. Now, if you see here, the PUs that I said, PU00, if you're all able to see my mouse cursor here gradually going up, PU00, 1, 2, 3, 4, all the way down till PU17. Now, these are the processing units. So there are 18 processing units. Generally speaking, in this case, 2 processing units are kept for redundancy in case of a failure. How do you switch over, etc. But generally, every other processing units are active cores, is what we call, and these are the ones which process threads and completes the task used for your computation requirements. So generally, as I said, 16 active cores and 2 spare cores to handle redundancy. That's how in this chip, it's how it is designed. Now, what are these L2? These are the caches or the memory, right? I mean, located alongside the cores. And if you see these L2, L202, L203, from here it starts. You see the way it's been aligned, 06, and then again 9, 10, 11, 12. So these are all the L2 cache or level 2 cache. In this case, there are 16 L2 cache. So what are they doing here? These allow the processors to quickly store information. The closer the cache is with respect to the processor, the far. Been hearing some background noise? Thank you. Can people who are not talking go on mute, please? Thank you so much. I'll continue. So the caches actually minimizes the data transfer. The closer, as I said, the caches to the processing unit, the faster you'll be able to retrieve information. The latency is low. Low latency is what generally everybody prefers in a design. So that's what we have seen. There are other elements to it. There is this DDR3 that we see on the side, which is actually to connect to external RAM. So that's something that we have here, one here, another here. I don't know where the third one is positioned.
कैमरा ऑन कर लो जरा, LP वाले ही ऑन कर ले थोड़ी देर कैमरा.
Can somebody speaking on with the mic open?
आपको राइट्स दे देता हूँ मैं, रुको.
Ajay
Can people
sir,
go on
your
mute?
mic is on, Ajay sir.
Okay,
Ajay
mic
sir,
on.
kindly switch off your mic. Thank you. Sorry for the disturbance, sir.
Okay. All right. Thank you. All right. So then we have networks and interconnects. Now, if you see the middle bar, what it says as X bar switch. Now that's the region that helps if you're all from some sort of infrastructure background. And if I give you an analogy, the enterprise bus, if you remember a traditional software architecture where you have a COBOL program, you have C, you have Java, and all of that, they can communicate through this enterprise bus, something similar. I'm not saying it's exactly the same. That's what this interconnect is all about. The network and interconnects here is represented by this X bar switch is all about. So that helps in passing the information between the processor and the cache. So that's what is maintained by these interconnects. And then I spoke about the SerDes and SerDes. It's nothing but a serializer and deserializer. It manages high-speed data across the internet, across the interconnects. So that's what the purpose of SerDes is. SerDes, as the name suggests, is serialization, deserialization of data. So now that we have all understood and we all should be happy that we have seen a chip, never get an opportunity to see a chip this closely, but at least we have managed to see a chip. So that's what it is. Now, how does this all stack up together, right? I mean, we've seen a chip, we've understood what is a node, what is a rack. If I walk into I don't know if LPU has a similar huge data center equivalent system, maybe. So how does this all look like, right? So we have a lot of infrastructure teams sitting in big companies. What happens when you walk in? So this is just an illustration to have all of you to start thinking on those lines. So we spoke about a chip. A single node board has, totally around 32 chips. As an example, I have given this here. Single node in this specific case has 32 compute chips. And we saw that each chip has 16 active cores, right? And why we are saying 16 is because, as I said, if you see here, the two of them are redundant ones, so not to be used. So each chip has got 16 active cores. So go by that math. So if you're looking at a node board, which has got 32 into 16, 512 cores. Now, there is a concept that I want to introduce called a rack. Now, what is a rack? A rack has 32 node boards here. Now, this on the screen that you see is the node board. And this you see here, it looks like if any of your houses, you might find a big cupboard equivalent. So something like that is what a rack is. So it has got 32 node boards nicely inserted. Now, these node boards multiply the cores that you have, 512. We're talking about 16,384 cores every rack. Now, how does a supercomputer look like, right? It's got so many racks put together. If you see this image number 7, too many racks put together, 7 of them, multi-rack system, if we count that, I think, yeah, it comes to 1, 2, 3, 4, 5, 6, 7, or 8. Yeah. So put them all together, there is a 96 racks. Imagine a huge room with 96 such rack systems. The total number of cores adds up to 1.57 million. So that's, and we're talking about our own systems where it runs like 4 cores or 8 cores or maximum 12 cores. Here we're talking about 1.57 million cores. That's the magnitude of computing power a high performance computing system typically has. And as I said, I love analogy, and I've given you this analogy again. A chip is like a worker in a factory. I mean, any a worker, if you imagine as an individual, that's a chip. He or she has his own abilities, ability to finish a job. So that's a chip. Now, a team of workers in an assembly line, imagine a factory, you're doing industrialization, big assembly line. All of the workers put together is the node. An example of a node board that we spoke about, many workers in an assembly line forms a node. Now you put all these nodes together, it's a department in a factory. A department, one department with multiple teams is typically a rack. The rack that you see here on this slide numbers or this number 6 here, it's like that. A rack is like a department in a factory, multiple assembly lines, multiple nodes, multiple workers standing there. Now a factory has many departments, right? So all of them put together is what a cluster is. So that's the magnitude of what one could imagine a HPC system is all about. So I hope you got an idea of what it is. This is a busy slide. I know many of you may be experts on what a CPU, GPU is, but I just wanted to give you a feel for this because this is something that goes in everyone's mind. Why can't I do this with a CPU? You said about FPGA. It sounds a very difficult acronym to remember, but why is that used? Why can't I use a GPU? So just a quick glance on the slide. CPU, anybody can, it's a general purpose. I can do this, but can I do complex tasks? No, that's where thousands of cores are required, which is where a GPU comes in. And I mentioned to you about FPGA matrix multiplication. If you're a mathematics expert, you generally find it difficult. So that's where specific jobs and FPGA is what can be used for. Serial processing is a CPU, parallel processing is a GPU, and very custom hardware is implemented. And in fact, there is specific coding for an FPGA. You can reprogram a logic gates if you're from the electrical, electronics, computer science background as well. You can program it in such a manner to effectively complete a task and then reprogram it and do another task, and which is where these FPGAs comes in. Performance is generally good for a CPU, but if you want excellent performance, GPUs are what is used, and FPGAs are very, very specific in nature. The other important variation of all of this is the cost, right? I mean, everybody who are working in large enterprises or even for universities where we need to decide, should I buy an FPGA? Should I manage with GPU? FPGAs are generally costly unless you are doing exhaustive research on a specific area compared to the other two. Of course, GPUs are also expensive. You don't need a program in a specific C++ or a C program to code in such a manner that you push forward for a parallel computing in a CPU. Whereas in a GPU, you really need to have that additional skills, and it becomes extremely complex in FPGA. So that's the sort of general view that I wanted to gather here or through the slide for all of you. Let's quickly move on to, we all like to see, right? I've built up so much about what high performance computing is all about. So let me know, what are the HPC systems? Sita ji, please bring that up. So that's the question that we have, right? So that's what I wanted to bring that. What are the HPC systems? The top 5, there are many. The ones that you see on the screen, this is El Capitan, then there is Frontier, Aurora, Eagle, and HPC-X. Just observe the kind of cores, 11 million cores, 9 million, in that range is what we're talking about, these cores. And look at the power consumption. I have some computation for all of you to appreciate the sort of, or relate to the power consumption of these gigantic machines. The right-hand side, this is again an illustration directly from top500.org, folks. You can always go to that website, and there are multiple combinations. But as I said, this is foundational introduction of what HPC is. I've kept it to answer those curious questions that we always have, right? Hey, which countries are using, where is India in it? It's a natural question that comes up in your mind. In this list, India is not there, but India is doing very well. A lot of effort by the government to bring in the best of GPUs, and good work is happening on the HPC front as well. But as we see here from the pie chart that we have here, naturally United States and China are leading, followed by Japan in terms of the country's share of these HPC systems. Very, very high level. Where are these HPC systems being used? Predominantly in the several industries. It cuts across the industries. Now, are these industries building applications and releasing it into commercial products or for commercial need? Maybe, may not be. I don't have that information with me. I was desperate to figure that out. I don't know. But then beyond that, research, most of the universities, and perhaps I'm sure LPU to some extent would be also using it. Academic usage for HPCs are what we are seeing. Government usage is very much there, and the rest makes up the remaining part of the pie. Now, this is a very, very interesting slide. A lot of data, but be with me and you will understand the power of what HPCs are all about. Now, a high-end gaming laptop, I'm sure you or your sibling or maybe your children would be doing a lot of gaming. And if you are in that sort of a mode, a typical high-end laptop that we all use in our systems, it uses 8 to 16 cores. 8 to 16 cores. And what is the capacity of that? It's measured, as I said earlier, in floating point operations, TFLOPS, 0.1 teraflops. Now, if you really compare that with El Capitan, now look at the numbers, and this is the same number that you saw in the previous slide, right? 11 million, and it translates to 1742 petaflops. What it simply means is it's 17.42 million times more powerful than the gaming laptop that you may have at your homes. That's the sort of 17.42 million times. Let's take a real world example and figure out what does it mean. Now, this is, if I have a standard laptop, folks, if we all use our laptops, MacBooks, I'm a fan of Apple, love what Apple offers, like probably many of you. A standard laptop, typically, if you wanted to do a weather forecasting simulation, take 1 square kilometer area of weather data that you might have for a single day, one day we are talking about. A standard laptop would be able to synthesize your weather data and come up with weather forecasting with all the algorithms. We don't get into the software part of it. We're talking about hardware here. So 30 minutes to build some basic models. Now, if you take an El Capitan or a Frontier, the entire planet's weather system with multiple grid points every few meters. A grid point, the smaller the grid, the better the accuracy of your weather predictions. It takes for a week that you wanted to predict for the entire planet, not your 1 square kilometer. It will be able to do it in less than an hour. And that's the power of what we're talking about, such HPC systems. Let's jump into another example here. If you're looking at genomics, and I'm not talking about the world genome of every single people living on Mother Earth, no. We are talking about a human genome, and let's say I have 100 GB of data. 100 GB is not bad, right? It's a normal data that we have, and it takes 2 weeks for a normal laptop to process that. An El Capitan, for an entire population, 1 million genomes, in a single day, it has this ability to process it. So that's the sort of a difference that we have. I've just given one other example here. My very own M2 chip, I just Googled up and figured out. I've used it for such a long time, my MacBook, but I didn't know that it had 3.6 teraflops per second, from a capacity of operations that it could do. Now, if you compare it with El Capitan is 500,000 times more powerful. What it simply means that if I put my system to do some mega operation, it will take 1 year, whereas El Capitan will be able to do it 1.08 minutes, folks. So that's the power of high HPC systems. Energy is a very important element. It doesn't mean that more power means it's consuming a lot of energy. It's another area that need to be looked at. Not a lot of energy efficient HPC systems are being built. I'll talk about it when I come again on the last day, I believe, in terms of the future of HPC, quantum computing, and all of that. But just gather this thought in your mind that a typical laptop is around 30 to 70 watts. I've taken an average of 50 watts. We saw the numbers of El Capitan. It consumes 29,581 kilowatts. So what does it mean in simple way? I just divided by, what is the number of laptops it takes. Close to around 600,000 laptops. The capacity of 600,000 laptops, I don't know how much of a room that it's going to occupy. That's the sort of energy that an El Capitan does. Is this still high? Maybe. That's where liquid cooling and all those concepts are coming in to reduce and prepare environmentally friendly, sustainable HPC systems. That's a topic, as I said, on Feb 1 when I come back and talk about it. But this, I believe, gives sort of an idea. I just wanted to take a check from all of you. Is it all going in terms of understanding the stuff? So that, I can now progress along to the next part of my session. All good? Just a thumbs up here and there should be good enough.
So
Thank you so much.
can we ask one question to them so that we can find out whether it is going good with them or not?
Okay, sure, please.
We can ask questions and give them 1 minute to answer. The link is in. I request everyone to just open the link, answer the question, and we'll find out and we'll show you that how many of you answered it correctly, how many you are looking for the second chance. The link is in. Yeah, Mr. Sunil Rathod. You give thumbs up when you answer. Let's have 76 thumbs ups. Yeah, there are a lot of thumbs up coming. Great, great. A lot of hands, yellow hands coming out. I like it. This is one of the questions of the gamification mode. It may be the question which can decide your award. Every question is important.
Okay. Mr. Ajay, whenever you want me to continue, I can proceed. Shall I continue, Mr. Ajay?
Sir, I wish the people are answering the questions. So give us 1 more minute.
Sure.
1 more
Thank
minute.
you. Sure.
So Dr. Rahul Desai, Dr. Sangeeta, Dr. Mohit Arora, Navjot Kaur, ma'am has also answered. Sunil Rathod. I want more answers. Are you answering? I hope it is you understood. My colleagues have understood what we want to do. Is it visible? I think it is visible. Where is the link? Link is, I answer, where is the link? Link is there on the chat, not in Q&A. It is on the chat. Link is on the chat. Okay.
Shall we go ahead, Ajay sir?
Yes, ma'am.
Okay. Thank you. Thank you, Mr. Ajay. And let's quickly get on to our next part of understanding HPC, high performance computing. Just take a step back. So what we have all seen, the word that I would have, if somebody had done a machine learning algorithm on the text, voice to text conversion using one of those algorithm, the big algorithm models that we have, Whisper as an example. Uh, Parallel would have been the overused word. We would have looked at nodes, clusters is something that I would have used. Exabytes, I've continuously kept using that. So if you create a word cloud of that, these would be what would normally come out. So with that, let's quickly jump to a few more deep dives, little bit of deep dive, not too much, into the application areas. At a very high level, we saw research, academics, where it is used. Again, same from the same source that I have picked up to share with all of you. Research is predominantly dominating in terms of the work that is being done, followed by cloud service. I was surprised to see, and I don't have any answer for it, why the application area on medicine, because so much is happening on the genomic fronts. One of the clusters, one of the HPCs owned by Japan, has been used for the COVID-19 vaccine simulation. So when that was there, why still medicine is showing very poor? I do not know. As I said, I don't have the answer. This is the data speaks for itself. Maybe there's much more to be done on the medicine side, genomics, drug discovery, on the pharma side, so much application HPCs have. But largely spread out is what the usage of application area of HPCs are. Top vendors, needless to say, you can all figure that out, what those vendors are on the screen. Now here, I have a love affair with Max in some form. I really like to get into the details to see what the numbers have to say. So what I have done is just to give you a feel of what's this massiveness of data that we are talking about. So now if you see here on this table on the right-hand side, I've just picked an example to illustrate the cores, 11 million cores, 9 million cores. These are the numbers that we saw on a previous table, right? But gaming laptop, even if I pick up 16 cores, if I do a simple comparison of, if I try to plot this, you would imagine you wouldn't even see where a gaming laptop is. So naturally, you need to do a logarithmic scale to really put a meaningful comparison. So I just have done that, and not just for cores, I've done that for your Rmax. We spoke about what Rmax in petaflops is on a logarithmic scale, and also the power consumption, just to see how these are compared to on a logarithmic scale to a gaming laptop, right? So if you see here, it's minuscule, these huge tall structures. Almost, the top ones have a similar number of cores, except a few which kind of drop, like Eagle is 2 as compared to El Capitan 11. But from an Rmax capacity, almost we see something similar numbers here, and also from a power consumption as compared to a gaming laptop that you see here. So in summary, whatever a gaming laptop, a task given to a gaming laptop, and if it takes millions of years, an El Capitan, which is a high performance computing system, would be able to do that in 1 second. Again, don't ask me what is the nature of the task. This is being explained to give you an illustration of the power of these HPC systems, folks. Okay. Not a fan of history, but I was also to talk about how did HPCs evolve. So I've just kept one slide to give you a feel of what it is. It's straightforward. It's always nice to look back and see and do the right things. History, I feel personally that way. So it's first supercomputers were there in the 40s and 60s. ENIAC, I should have probably asked as a question, Ajay, what does ENIAC stand for as a quiz question? So those were the times where the first supercomputers slowly started evolving, largely used for military operations during the world wars of that time. And if you really look at the ability of flops here, we're talking about kiloflops. We are in the age of 1940s and 1960s. And gradually, the 75, 1990 era, I think there's a very good article about Seymour Cray. Some of the computer science specialists would know whom I'm referring to, a brilliant mind. That was the Cray era where 6600, I think that was one of those systems that got built, and other CDC computers. The application in this era, from a supercomputer perspective, evolved from not just military driven to computer fluid dynamics, climate modeling, earthquake detection, oil exploration, etc. So that's where 1975 to 1990, the next evolution of HPCs were. Then came the era, the millennial plus, where I would call it as the cluster era, where we have systems with distributed memory and dedicated memory. I have analogies for that as well. Very soon you will be able to see that. Commodity hardware was being built by a lot of these vendors. HPCs as a system started to really come up in a big way. Some of the names, even I myself am hearing it for the first time. Intel IPC, this is a known name. Hypercube was pretty good. NASA's HPCs for space simulation started to come up in a big way. So that's the era of cluster era, is what I would call. To what today we are seeing is an era of GPUs, hybrid era, and I don't know what, as we are speaking, NVIDIA is doing in terms of building their huge stack, and we're talking about sending stuff to space. It's an era of exascale computing. There's a lot happening, and please do read about what India is doing. It's very much in a progressive way of looking at and trying to build huge HPC systems. Government of India, as I said earlier, is planning a lot on that front. So that's on the history. And how did this shift happen over a period of time? What was the compelling reason? If you really look at what I just said in the previous slide, there has been a shift in the goals of supercomputer evolution. Initially, it started off with, I need to solve military problems. If you're a fan of Avengers, Captain America, and all of that, evolution, you would know that, those Germans used to build such sort of systems, and largely for satisfying my military goals. Now, from there, it looked into, can I have a system that solves more than one problem? And which is the example of Fugaku, which was used for COVID-19 spread check, the models that they built, as well as Japan, as we all know, is known for its tsunamis and earthquakes, so simulating tsunamis, and also it's used for drug discovery within the same system. So multidisciplinary need for a supercomputer from one single task. That's what has resulted in the evolution that we have seen. What is the second? The second one is, can I have a system which is highly efficient in its energy consumption? Can I produce environmental friendly liquid cooling system? We just saw a number around 27,000 plus kilowatt. Can it consume lesser energy? Can we make this earth much more safer, less warmer? So those are what had resulted in, still the progress is on in trying to build highly energy efficient HPC systems. Cloud, I think cloud has changed everybody's life, right? I mean, I'm sure many of you would agree to me on this. So the HPCs on the cloud, it's like democratizing. Everybody can use a HPC. Ability to scale is going to be very high. People across the globe can access it. So that's another drive towards what we have seen in terms of HPC evolution over the years. Analogy, that's something which I really like. And we will talk about the notion which I kept it till the last, before we dive down to the use cases, before I finish off my session. Now, the most important concept, and I do know when I've seen the agenda of other panelists who are going to talk about it, they are going to deep dive into each of this, but at a very high level, and if you continue to be on those sessions, this is a primer for you to know. HPC architectures generally are shared memory and distributed memory. Now, what is this shared memory? For this session, I consciously went to some of the top vision models to figure out, and prompted it enough to get you what I actually wanted all of you to see. It's like all these processors, these humans, as you see on the screen, sitting and trying to solve a puzzle. They are trying to solve a simple puzzle. And now if you see a person comes in and tries to put in his version of the puzzle, but there will be somebody else trying to do that, right? So there is that sort of a contention that happens, but everyone in a shared memory environment, as you see here, there is a single memory space and they're all trying to do the same job together. So that's a general notion that you need to carry away from this slide on what shared memory system is all about. Now, what are the applications for shared memory? You could look at for weather forecasting of a single region. So you divide that into multiple smaller parts, put them all together, and then they access a common shared memory location, and you'll be able to simulate the weather for the entire region. So that's a classical example. Advantages: very easy shared memory systems. Nothing much to do, low overheads, and because it's shared memory and all the processors, as I said, imagine that these guys are all your the humans here are all your processors. There is a latency is low because they're all accessing the shared memory, right? So that's the advantage. Disadvantage is naturally you might have figured out. What if I wanted to, bring in another processor, bringing another person, or am I really utilizing the capacity of each of them to do the job? Another person is waiting until his adjacent processor is finishing off the job. So there are these scalability issues and constraints on memory if you're looking at a shared memory architecture. So that's about shared memories in a very simplified fashion. Now, what is distributed memory? Now, if I tell you I have a big puzzle to solve, these are parts on the left hand side, these are on the right hand side, these are at the bottom, these are at the side. Put them all together, bring them to me. That's it. That's what is a distributed memory in a very simplified way. Each of them have their own tables, which is their own memory, and then they try to solve. But then how do I communicate? Hey, I have completed my part. How does that communication happen? And that's where, if you recollect, I was referring to a notion called interconnect, which is the MPI protocol, and that's how these nodes or these different sets are try to communicate, which is the message processing interface, or MPI is all about. Now, there are advantages and disadvantages here too. So scalability was a disadvantage previously here, as you saw here in the shared memory. Distributed memory, you don't have a scalability issue. It can handle any large scale problem because I need to put another table with a few processors, give it its own resources there. They will do the job. So that's how distributed memory is structured, very cost effective. I can have, if you're able to see my mouse scrolling, this corner seat of person working on a completely different commodity, Lenovo's HPC, and here I can have somebody else. Here I can have some other vendor. So that sort of distribution, and whichever is cost effective scaling can be achieved. Fault tolerance is very high in distributed memory, whereas in the disadvantages are very much there. What is the disadvantage? As I said, the communication between these two, internode communication, is a big challenge. It's a programming challenge, actually. If you are from the Fortran or C++ side, now how do you ensure and communicate that this job is being done? So that is an issue. And the more complex it gets, the data transfer between the nodes also become an overhead. So that's the distributed memory simplified. And you need the best of both the worlds. The only answer we all know is hybrid, right? When you have both these things coming together, where you need to get the best of flexibility and performance, and from a distributed memory and a shared memory, you come to a hybrid model. You have both of them. It's something which is pretty much in use largely for deep learning. The large language models training that we see, GPT's training that we see, and I'm assuming, and I don't know, I have not seen this. Sam Altman and team perhaps would have got a hybrid hybrid HPC in his setup to train those huge amounts of data to come up with those foundational models. So that's the hybrid version of HPC architectures. A quick look at it in one single slide. So which we saw about a lot of these HPC systems. Fugaku is the hybrid one, which we just spoke about, right? In Japan, what it does using for drug discovery, the pandemic that we had some time back. So that's something which is Fugaku is hybrid. Another hybrid exascale computing power that has got is El Capitan. The older ones used something called vector-based memory system, which is again from Japan. And there are still a few shared memory systems that are still put in use today. So that's how it is. But largely, this is my personal view. The tendency of HPCs are moving towards hybrid architectures. I think we will spend the last 5 to 10 minutes to quickly go through a few use cases, and then we can end there. The first two of the use cases, I've just taken it in pairs. The first one on the left-hand side that you see is around how do we use HPC for weather and climate research. If you see what is being done is the entire surface of the earth, they break it down into multiple grids. The smaller the grid, the accuracy is quite high, and then they calculate all the parameters related to any weather pattern, right? The temperature, humidity, wind speed. So that's typically so much of information, so many grids, and then again the geography that we are looking at. So that's the sort of massive data sets that HPC process. An example is ECMWF, European Center for Medium Range Weather Forecast, uses it's a HPC system primarily deployed for weather and climate research. Obviously, we needless to say about the benefits, so I'll skip that. Biology and genomics, there are, according to me, there's a lot happening on the space. HPC is also used for looking at the AlphaFold, which is a protein folding simulation. The Human Genome Project, if some of you might have heard about it, it's also have used HPC. There are specific algorithms like basic local alignment search tool. I've heard it for the first time when I was trying to put this through. I don't come from the medicine field, but very interesting to read about this. So that's used for comparing DNAs and huge amounts of data that we spoke about. It's not possible without the massive computational power of HPCs. So those are the first two use cases. We have the next set of use cases, again, starting with the pharma side, drug discovery. We spoke about molecule interaction simulation. All of that is possible to come up at that right drug, which will be mapped to a protein. So that's something which is possible through HPC systems. Pfizer is using it in a big way as well. Energy exploration is another area where we are looking at or identifying oil and gas reserves. How do I know that there is a pool of such resources available? So that simulation, drilling the paths, and all of that is being done. Chevron is a company which uses heavily HPC systems to process that information. To all their resource exploration is happening related to identifying a resource for energy exploration. Chevron is very much into it. HPC systems are used there. 5 and 6 and 7 and 8, and we would largely come to finish. Aerospace engineering. It's again, I'm not saying that ISRO doesn't use it. ISRO probably would be using it, but NASA typically uses it for spacecraft design and testing, running multiple simulations that they need. So all of that is typically used in the aerospace engineering. My favorite side, finance, where I generally come from, Monte Carlo simulations. Many of you may know what it is. And I spoke about high frequency transactions, right? High frequency trades, HFTs, to detect frauds occurrence. In nanoseconds, transactions are happening. How do we detect that? Unless you have powerful computations able to provide real-time analytics, impossible to predict. So that is where in finance area, where HPC systems are largely used. We'll finish off with 7 and 8 here. And again, an example of medicine related to where, for COVID-19 vaccination, we had HPC. COVID-19 itself was a big challenge for all of us. How do you determine the vaccine efficiency, right? A lot of simulations need to be done. So HPC was very much used there. And on the mechanical side, computational fluid dynamics. What I read it for the first time when I was figuring this out, the applications Tesla seemingly is using to build their aerodynamic friendly cars. Right. So for that, to simulate all of that is also where HPC, is put in bigger use. So with that, I come to the end of this presentation, and I know we have another one at 8 o'clock. So just conscious of time. I believe you had the whole intent, as I said, was to give you a flavor of what HPC, set the stone for the future talks where they will deep dive into each of these topics. And I hope you had some level of takeaway for this. It's a huge field, folks, very much interesting. I come from the software, machine learning, generative AI, immersive text space. This is an area which has always interested me, and that's what I had presented to all of you. Hope you found it interesting and a lot of learning from this session. Thank you. Back to you, Mr. Ajay.
I just have one question as actually it was a great session. I just want to ask you about how HPC systems are going to help us in attaining sustainable goals as such. There are 17 out of them. How many are being catered or how many are can be catered as such?
So you're talking about which of these HPC systems can be used for sustainable goals, which are
Right.
environmental friendly, don't consume so much of energy, if that's
Right.
what you're leading to.
Yes, sir. Yeah.
Yeah, so I think there is a lot of research going on that front, Mr. Jai. In fact, very recently, I think Meta had come up with their research on building a HPC system where they literally on Instagram, I think they were looking at how a cooling agent, automatically does multiple jobs in terms of reducing the energy consumption. When too much processing happens, naturally, even our systems make that sound, right? Your fan processing speed runs, right? So how do you use the right liquid to cool and ensure that the energy consumption is lower? So there are a lot of research happening. Now, which system specifically, if you ask me, I don't have a pointed answer, and that's where the research is heading to in terms of building the right system for, which will also be environmentally sustainable.
Which systems that cannot be answered that can be explored, but yes, you gave a ray of that. Yes, something is being done, and very soon we
Something
are
is being
going
done.
to find the results also. Great, sir. Any questions from the participants? You can tell me. I can make you a panelist, and you can answer ask the questions. Whereas those who are already accepted my offer, I wish you should be asking at least one or two questions.
Yes, please feel free to ask a question. If I know the answer, I'm going to say. If otherwise, I'll point you to at least for more research.
Good evening, sir. So there's one question highlighted, like how can we use HPC in finding out real and fake news in real time?
Mhm.
Is it somehow it could have its application in this area?
Um, Real and fake news. I sometime back had done, I would say, academic project on that front, ma'am.
Right, sir.
I didn't see, it all boils down to the extent of data that you have, right? I mean, if you are telling me that we will pick up the entire X, and then use it with all this information to process and detect, then we are talking about huge billions of data to be processed and figuring out. There's an algorithm that need to run. So there, I think HPC systems would definitely be a good use case, is my personal view. But what I was trying to get to is if your volume of data is small and if you're only looking at, let's say, I work from company A and I wanted to know, I've launched a new product and I wanted to know on Instagram and other such social media, between this period to this period, how are customers responding to my product? And I want to use that information to feed into my marketing and customer service teams to help them, close the communication gap or enhance my product. And that we are talking about lesser amount of data. Again, depends on the use case to use case basis. So that was the use case that I had done to simulate it. And if it's a minimal problem to be solved, I don't think so. We need a HPC system, ma'am. But as I said, if the scale is large, and I think recently one of those social media, without naming it, it's not appropriate in a public forum. They're going to stop checking whether the news is fake or not, right? I don't know why they are stopping it, but if you do that, you need to process huge amounts of data to come to the conclusion. And I think HPC system is the right solution for it, ma'am.
Right, sir. Thank you so much, sir.
Thank you.
One more question, sir, from Dr. Kamal Kishore. That how can we use HPC in agriculture?
Oh, okay. Um, Good question, and very much pertaining to our Indian context because of what we are as a country. Um, I think I don't know. I know an example, and I may not be in a position to give you a complete answer for it. I know a company here in Bangalore who were looking for giving the farmer the best price of a product based upon the various mandis spread across a region. So if I have a cotton produce, if I have another crops produce, so what is the right price that I need to do? So they have done a phenomenal exercise. They went to multiple places around Karnataka and then figured out and then created a huge data set. So for such requirements, if the volume of data, again, it comes down to what do you want, right? If the volume of data is very high and you need instantaneous responses to be provided, processing computing power is very high. To assist a farmer through an app, which is an edge device, right? All the processing happens on central server. The notification goes to an app saying this is the right price for a product. Maybe that's a good use case. The other one that I could think of, and I may be wrong, I'm not an expert, apologies on the agriculture side, but what I could think of is trying to discover whether a specific crop is infested or not. That sort of imaging that we need to do, study multiple photos, and if it is of a specific pattern, this is the fertilizer that need to be applied. That could be a good use case that we could look at for HPC. The last one, I know this is done in somewhere in Andhra or Telangana. They are trying to find out is a land arable or not by scanning huge using photographs, aerial photographs through drones, so that they could really spot the right space and a right place to plant their crops. So again, huge amount of data points from imagery, which are the photos of huge amounts of land, and then trying to detect and process information is not easy. So that's another space I think HPC could be used.
That's great,
Excuse
sir.
me.
Yeah.
Sir,
Yeah, ma'am.
nowadays we are having automatic vehicles. Like it's a real-time data access and all. So somehow can we relate it that it's the another application where such systems can be used? Because it's the
Mhm.
time data maybe.
So are you talking about autonomous vehicle where
Correct.
it needs to process, which is
Right.
driverless? You're talking about
Right,
that,
right,
right?
right. Correct, sir.
Which is definitely Tesla is using it.
Correct.
And see, there are two aspects to it, ma'am. One is, does your automobile itself has inherent capacity to process what is an object which is in front of me to take an instant decision? That processing power definitely is inbuilt within the automobile. But there are certain times where you will have to go back and process that information on a central system and then instantly get back the results, right? So for such needs, I think HPC. So it's a combination of HPC sitting locally and then somewhere in the central server. So that real-time analytics can be made available to the. There's no driver here for the autonomous vehicles to not get into accidents. So definitely, it's a right use case, ma'am.
Right, sir. Thank you so much, sir.
One person, Dr. Prashant, is asking that what are the measures taken for doing an intensive job on HPC?
What are the major? Can you please repeat?
Measures, what are
Measures.
the measures, yeah, that can be taken while doing an intensive job on HPC?
Internship job. So as an intern,
Intensive, an
intensive.
intense,
Okay.
yeah,
Intensive job. Okay. Sorry. I was
yeah.
just wanting to clarify. Um, See, I think the definition of should I use HPC or not depends on your application. If you are looking at building an application which is demanding high compute processing, it demands scalability. You may want to expand it. I think that would be another criteria that you could look at. And then we spoke about the memory usage, right? Shared versus distributed. I think that will be another consideration if you really wanted to build high capacity HPC systems. So that will be another area of research that you would want to look at. So if you really ask this to an infrastructure head, and if you say, I want to set up a global capability center in, say, I think you guys are from Jalandhar, if you wanted to set it up, these are the number of people who will be accessing those systems. So it depends on problem to problem statements. What do I want? How should my data center look like? What should be the computing capacity? What are my SLAs? How soon I need to respond to any request, where a teacher or a student is trying to access system. So all of these aspects need to be studied. The problem need to be identified before you really come up with defining whether you need shared, distributed, or hybrid, and other aspects that I mentioned about HPC.
That's great, sir. One last question, Dr. Prashant Lakdawala. He says, what parallels can be drawn between HPC architecture and quantum computers? What
Oh.
parallels can be drawn between
John.
HPC architecture and quantum computers?
Okay. I think it's more on quantum computing is, I think the kind of problems it is expected to solve, the computations are very, very intensive at an atomic level. I don't know if a quantum computing will today's HPC, will it really solve quantum computing issues? Do they have the power or not? I would not know, because today classical computing and quantum computers are what we are talking about from an evolution perspective. Maybe HPCs need to really grow up much more than the exabytes, I would say so, for solving any quantum computing related problems. So that's what I would say as a difference. Not much of it. I don't think so. Even an El Capitan today can solve a quantum computing problem. In fact, this was very recently in the news where they said they still need high-end processors to really go at the atomic level in terms of identifying the multiple states, which are what is known of quantum computers. So long way to go to really have systems capable to perform quantum computing operations.
Thanks a lot, sir. There are a volley of questions that are coming, but seeing the time constraint, all of us would like to thank you for an excellent beginning of the sessions, and we hope everyone will give. I request everyone, please have a flow of likes and loves so that we can give. That's in return, sir, what you see about the session.
Thank you so much. Just wanted to conclude by saying there's so much to learn, so much things are happening every day in and day out. It's a field that's evolving. So do a lot of research, do study about it. There are excellent sites to learn about HPC. So I'm sure at some stage, India will come up in the pie chart that you saw as one of those strong players in HPC side. Thank you so much. Back to you, sir.
Thanks a lot, sir. Have a great time, and we'll see you, at the end of the
Feb 1st.
session, Feb 1.
Thank you.
With, I think, your knowledge, your skills, as much as we can explore.
Sure.
So thank you very much.
Thank you.
And
Thank you so much.
have a great time, sir.
Thank you so much. Take care. Cheers. Bye.
In the meantime, the participants, please don't go, as sir was going in a flow, so I did not ask you any question. But now there are two questions I'm putting on everyone. Means maybe there was a problem in the first time. So the first question is there for everyone, and putting another one. And I'm telling you guys, we do in LPU, even we do a lot of corporate trainings to public sectors and private sectors and academic outreach and in-house faculty development programs, and we do this gamification. And I assure you, if you win, your prize will reach your house. So one form I have shared, another I'm going to share. So there are two forms, and there was a problem in attendance. Burkar Saab said there was a problem in attendance. So we are going to share the attendance form once again. I'm going to share the attendance form once again. But in the meantime, I'm sharing one more question related to HPC systems. right? There is a link which is coming up. So there are two links. Another question came up. My computer says battery is 100% charged. So there are two links. Please go through the links, everyone, and I will show you the results. Before Avdesh Shukla comes. Avdesh ji, are you there? No, it is visible now here. Can anyone say, Navjot ma'am, are the links visible on the chat now? Anyone? Nihar Pradhan, Professor Abhishek.
Yes, sir, it's visible. We
On
are
the
able to
chat to
answer.
everyone.
Right.
So please
Right.
go through the links. Let us make it more interesting. So I can see quiz 1. Yeah, response is going to 40. Great. So the two quizzes are already set. Anyone who is having problem in attendance, please let me know on chat. I know I'm like you only. It is one of the important aspects of our lives. So we'll not let you down.
Online.
Yeah, Mr. Srinivasu. Dr. Saab, please.
How to give attendance online or hello?
Attendance is online. I will put the link on chat. Don't worry.
Okay.
I'm giving you once again. Don't worry. Please answer
Sir, not able to hear you.
Okay. Sir, good evening. It's good to see you once again, sir.
Thank you so much, sir. Thank you so much. Good evening, sir. Good evening.
I just want to share some results of the previous quizzes.
No issues, sir.
The
You
quiz,
can.
I will just share my this thing for a while, and then we can show you. So there were the things are very, very exciting. The first quiz, let me show you. Chrome tab quiz. Is it visible? And we can see the first quiz, 92% people have given the right answer. 93, in fact. Great. It is about the first quiz. Means out of 55, 51 are correct responses. So you will make our decisions very difficult. Great. So let us see about quiz 2. Quiz 2 has less responses. And up till now, %95 says yes, we can win. Great, sir. So, ladies and gentlemen, keep on attempting these quizzes, keep on studying, because we have another person on board. And why I was very, very familiar with him, because I know him from years. He is Mr. Avdesh Kumar Sukla, highly skilled cybersecurity professional with extensive knowledge and experience in domain of cybersecurity. He is a principal security consultant at Quick Heal, where he provides expert guidance and advice on security related issues. He holds a variety of CompTIA Pen Test Plus, CompTIA CYSA Plus. In addition to his CompTIA certification, he is also certified EC Council Instructor and a certified ethical hacker. He is a Jupyter Network Certified Associate, Zunos, and has a wealth of experience in a variety of security-related areas, including vulnerability assessments, penetration testing, and network monitoring. So without any ado, I would like to welcome you on board, sir.
Thank you so much, sir. Thank you so much for the wonderful introduction and giving me the opportunity to discuss the knowledge and share the industry experience with lot of respected professors, teachers, and all many colleagues who are available over here. So I have seen that in the previous session, they have gone through the various fundamental of HPC, high performance computing. So in this particular session, we will discuss in detail about cluster architecture and try to do some hands-on practical and demonstration to set up HPC architecture. So I will try to make this session as much as possible to engage everyone and try to create a situation so you can also able to perform some hands-on practicals. Once my screen is visible, sir, kindly give me the consent regarding the same.
It is, sir. It is visible.
Thank you. So right now we are going to discuss about HPC system component and cluster architecture. So when we're talking about cluster architecture, first we need to understand the difference between cluster and grid. Then we are coming on the HPC because in the previous session, sir has already discussed in detail about what is HPC, what are the basic definition of HPC, each and everything. I will try to relate because a lot of professors are here. So I will try to relate the use of high performance computing in the domain of security, how we can enhance the security and how it's a threat for the security when the high performance computing comes into the picture. So we are going to start at any point. If you're having the question at the end of the session, we will go through the Q&A, and I am happy to discuss various things with you guys related to doubts and question in this particular topic. So sir has already explained in detail that what is the high performance computing. So I just want to give you the brief idea, just a high level overview, that with the help of high performance computing, we are trying to solve a complex problem of every domain. Every domain. Sir has taken lot many examples from the finance department. I am highlighting the examples from the malware side. So if we will try to include high performance computing in the malware identification and analysis, this is one of the very good and prominent area of research, because timely identification and classification of threats help us to secure organization in much better way. So we will see that how much HPC is going to help us to securing the organization with the help of massive computation architecture. So we are very much clear. The purpose is solving the problem with the exceptional time within the nanosecond or the fraction of the second. The biggest phenomena of HPC that it is offers scalability that we discussed. The sir is discussed about the scalability. Specialized hardwares are utilized for giving the performance like that CPUs and GPUs. We will discuss in detail how CPUs and GPUs are different for handling those tasks. Applications. So the major applications which are very popular is weather forecasting, geoeconomics, artificial intelligence, malware identification and research, and solving some complex mathematical problem is also one of the very important feature of HPC. Now, what is the role of HPC in scientific research and industry? So, high performance computing having the capability to transform the era of research, because in the research, the biggest challenge is we required a result in the faster pace, and with the help of HPC, we can able to implement that thing actually. So it is going to accelerate the research. The first point which is highlighting it is telling about how we can accelerate the research. So HPC is having a massive computation power. So it is going to break down the problems and try to solve the problem in faster pace with the help of parallel processing. Big data analytics. So right now, if I will talk about India is one of the largest digital economy. And if I will talk about only fintech industry, financial technology industry, more than 110 billion users are using digital devices in India. Digital devices. So you can assume that how much massive data they are generating. So if we're talking about entire globe, in entire globe, the data production rate is very high, and handling that data, generating the result from that data, identifying the pattern from the data, doing the research in the domain of medical sciences, it is very tedious task. So HPC help out to performing all these analytics in the faster pace. So big data analytics is also one of the very prominent area where HPC role is very significantly high. Innovating the applications like that, training a large data. AI is next. We can say that we are shifting entire paradigm to AI. Either we are talking about the software industries or automobiles companies or any type of organization. Everyone is shifting toward the AI, and that required a very good data set training models, and the mechanism which can build a robust training model system in the faster pace. So innovation, various kind of application like the driverless car, or we can say that we have seen in India, n number of companies are providing the cars with having ADAS level 2. So how they are training their cars, the massive data is required because India is a very large country, and if we will see the diversity in the road infrastructure is highly different. Means in the mountains we having different kind of curves. So training their models so perfectly in the less amount of time, HPC plays a role for generating the data, handling the data, and training the models also. So we having a lot of scope in innovation and applications in the emerging technologies. Global collaboration is also one of the very important paradigm which I want to highlight. In COVID-19, like that, the research or medical research companies from the globe will get collided, and they want to perform a massive research like that. They want to test a lot of medicines, they want to generate a lot of data, they want to see many conclusions in very minimum amount of time. So this global collaboration is also very important part. HPC is going to help us to solving these kind of problems where the global collaboration and the massive amount of data is required. Economical growth, already lot of examples are taken from the fintech industry, so I don't want to highlight lot many things. Industrial optimization. So every industry need to be changed themselves. So industrial optimization help industries to improve design and optimize manufacturing process and enhance the efficiency. That is also very important role. Now coming on the overview of HPC system. So before coming to the overview of HPC system, I want to highlight two things. For that, I am going to add a blank slide where I can draw the diagram, and I will try to explain so you can able to relate the things. So when I'm talking about HPC core component, it is very important to understand cluster and grid. Cluster and grid. So when I'm talking about the cluster, so cluster is a collection of same or homogeneous type of system. So when I'm talking about the cluster, cluster is a collection of homogeneous type of system, and these cluster are located in geographically single location. Means if I will talking about that my cluster at LPU, so it containing 6 systems. Take an example from here. 1, so you can say that clusters which are centrally located, first thing, and what they containing all the system using the software as a Windows 10, just with a Windows 10, just example. So all the system are using same type of infrastructure. So what we did, we combined all the resources. So here I am just writing you that I having 7 core of CPU, 7 core of CPU, and 6 GB RAM, 6 GB RAM. All the system having same configuration, all the system having same configuration. So collectively, what I can say in this particular diagram, I can able to conclude that total I have 6 into 6, 36 GB RAM in entire cluster, 36 GB RAM. And if I'm talking about the first one, so 7 cores, 6 systems. So we having total 42 core of CPU, total 42 core of CPU. Now, if any user want to process any of his tasks, first this task come to this particular layer, and user will always having an illusion. Consider this is a master mode, master system, anything. So I'm just representing it as a master node. So if any user will see, what user can able to see, the capacity of this system is User is able to see the capacity is 42 CPU cores and 36 GB RAM. Means if user having some task which required 20 cores of CPU and which requires 16 GB of RAM. 16 GB of RAM. So the user will see this particular cluster and he will get satisfied. Yes, the cluster having the 42 cores and my requirement is 20 cores. That cluster having the 36 GB of RAM and my requirement is 16 GB. And once this query will come, now this middleware master node where the load balancer is attached. What is attached? Load balancer is attached, is distribute the work among multiple nodes. It is going to distribute the work among multiple nodes. Once these nodes will perform the computation, they will again give back to the master node, and master node is going to give result back to the user. So user is going to receive the result. This particular layer or master node is created an illusion in front of the user. Now, this is only possible if user is looking for a task which required Windows 10 as a platform. Means if any task is coming for the Linux operating system, this cluster is not able to satisfy. So what is the advantage of cluster? We can create a pool of resource, and that pool of resource is able to handle the task of user. The second, the advantage is pooling. The disadvantage is that it is containing homogeneous type of system. All the system having almost same kind of hardware infrastructure and same kind of software infrastructure. Second is they are not geographically dispersed. They are located in the central location. In any situation, if that location goes down, nobody can able to perform any kind of task because entire cluster goes down. There can be various calamities. There can be a various situation like that natural disaster will be there. There's some kind of power failure or some kind of industry control system failure, like that entire power grid of XYZ location goes down. So cluster which is working on that location is also goes down. So these are the challenges in the cluster. So for overcoming these challenges, we come with the new concept that is called grid. Again, grid contains different type of system, different type of systems. When I am saying that different type of system, or you can say that heterogeneous systems. So this is one advantage, and grid also support the distributed computing. Grid also support the distributed computing. So we having two features in the grid, which is not available in the cluster. Means grid can have some system of Windows also, some system of Linux also, some system of Android also, some system of Mac also, whatever is required. So grid is another mechanism which support distributed computing, and cluster is a mechanism. Yes, cluster is a homogeneous. Cluster is a homogeneous. Now, we are coming on the advantages and disadvantages of the same. In cluster, all the nodes are located in same locations. So communication among the nodes are very fast. Communication among the nodes are very fast because geographically they are located into the same location. In the case of grid, the nodes are located in different locations. So communication is not that much fast. So that's why when we talking about HPC, due to the communication speed and due to the communication ranges, HPC is more intended towards the cluster as compared to less intended toward the grid. So we can say that whenever talking about the HPC is talking about more about the clusters, less about the grids. Now, if someone say that we cannot implement HPC with the grid, no, we can implement, but The efficiency is not like that. So I will show you the several example if you will write down. Because all of you know that cloud is a distributed architecture. We having a distributed architecture in the cloud mechanism. So you can see that if you will search on the internet, AWS HPC cluster, they will provide you the proper service. I will show you the demonstration for the same. And if you will write down Azure HPC cluster, if you want to check it out, GCP also. So GCP is also going to provide you the HPC cluster. So using these clusters, you can perform your tasks. So what I said, they will try to provide the resources from one location because the high connectivity among the nodes is required. Because you can check from this example, how many cores are required? 20 cores. So if these systems are not connected with a high speed network, you cannot able to transform the task so rapidly. So user cannot able to understand that his task is solved by one machine or multiple machine. So this is the architecture of cluster and grid. And that's why the HPC high performance computing is more intended toward the cluster. If anyone having any doubt and question till this point, they can put in the chat box. And if everyone is good to go, just give Y in a chat box so we can proceed accordingly. I hope that, yes. Does homogeneity of the cluster is depend only upon? No. When I'm talking about the homogeneity, it is not dependent upon the only software. It is dependent upon software, hardware, everything. Just for the clarity and just giving you the high level example, I have taken as the operating system is the homogeneity part. So you can, yes. Anything means if either hardware architecture is different or software architecture is different, so we can call it as a heterogeneous system. Sir, how the nodes are connected in simple network? Star network? No, nodes, Nikhil, like that nodes, all the nodes are not connected in the star network. For internal nodes may be connected with the various mechanisms. They will follow whatever the network mechanisms are required. But yes, there is a master node. So you can say that all the cluster slave nodes are connected into the master node. If the master node goes down, then it's create a problem. With that respect, you can say that somewhere we are going to form a star topology. Anyone else having any question? Okay. So already have taken this particular overview. So just comes core component. So HPC is composed of computer node, storage system, interconnected and management software. Now tell me what is the role of this management software? So if you go one slide back, in this layer, what is working? Management software is working. Why? Because this management software will do the task distribution, reassembly of the task, and going to present to the user. Because as a user, we are not aware that which particular machine is solving our task and all. So it is important some management software is required in this particular architecture. Parallel computing. So parallel processing is which makes HPC is a system where multiple nodes are simultaneously solving a task. So we will say that there is a huge parallel processing. Yes, if you are configuring Hadoop with the similar, so it's a cluster-based system. If you're talking about the big data, then if you are configuring all the systems having same configuration, so you can say that it is a cluster. Tailored for specific need. So we can design the HPC system which is focused on a single domain like that. Weather prediction is one example. Fintech analysis HPC is another example. So you can include that. You can create a system and train that particular system according to your need. Again, coming cluster-based design. So I already explained you that a proper example of cluster and grid, you get the idea. So there are multiple real world examples are there, like that IBM Summit is there, Google Cloud HPC solution, and which is going to showcase the potential in the diverse domains. So we will see a few examples in detail. So HPC cluster, everyone aware about the definition, but we will take a high level overview from here. It is a centralized system. All the nodes shares workload, making cluster as a single powerful system. So in the diagram, you have seen that when end user will see, he cannot able to identify how many systems are running in the background. He can only able to identify what is the maximum capacity of that particular cluster. So core idea, utilize parallel processing to split tasks across multiple nodes. So you have seen that when task will come, task will get split across the multiple nodes, and multiple nodes are going to perform that task in the simultaneously. But remember one thing, clusters or grid is useful for those applications which is designed in such a manner that they are ready to run into the parallel environment. If that application is designed, it is dependent upon one and another, so it is not suitable for the HPC environment. So when we talking about the HPC environment, we need to write a code in such a manner so that particular thing which we are utilizing, that can be easily handled and executed into the HPC environment. Common uses we already discussed in the scientific research, in the financial modeling, artificial intelligence, and now even it is involved in the security solutions also. Scalability, so it having the capacity to scaling, either horizontal scaling or vertical scaling. You can scale the clusters according to your requirement. Now we are coming on the clusters component. What are the components of clusters? So first is head node. Sometimes it is also called master node. Sometimes it is also called admin node. So don't get confused. So I am going to draw a diagram over here. From the diagram, you will try to analyze that what kind of things will come. So try to understand. This is the user. User is always going to coordinate with head node. HN is going to represent the head node. And in the head node, in the back end, we considered this is a cluster. Cluster can be contain any kind of node. So if I were talking about, this is a computational cluster. So all the computational resources are there. So there are three resources. Sometime load balancer and scheduler is a part of this head node, or sometime another system is acting as a load balancer and scheduler. So first, user interact with the head node. Head node will pass that request to the load balancer and scheduler. Then load balancer and scheduler will redistribute the task among available devices inside the cluster. So head node is a centralized node that manages the task, scheduling, and monitoring of entire cluster. Sometimes the question will be asked, can we segregate all these responsibilities? Yes, we can segregate it. Second, compute nodes. So you can also call them as the slave nodes. They will perform the majority of computational tasks, typically designed with the high performance CPUs and GPUs. So CPUs and GPUs, all of you familiar that these are the processing unit. One is central processing, another one is the graphical processing unit. Storage system. So we will see the example when I am going to implement. So it is going to follow the criteria of storage system, and what kind of storage system is required. NFS kind of, all of you familiar with the network file system, because what we are doing, we are storing over the network. We are not aware about that on which system we are storing the data. So we have a storage cluster. So it may be available on drive 1 also, drive 2 also, drive 3 also, and how entire storage is connected with each other with the help of network file share. The storage devices are connected with each other. Or we can take an example of network attached storage, or we can take example of parallel file system, PFS. It is also going to help to distribute the storage into multiple devices, and it will keep track of it is very important. When user will retrieve the data, user want to retrieve the data in proper order in which is stored into the system. So it is going to help out. And NAS is required, parallel file system or network file system is required to organizing data in such a manner. So whenever it is required, it is retrieved into the proper manner. Power and cooling system, that is also a component, core component, because if you want the availability of your high performance computing system, you need to take care of this. If you will not design your HPC center properly with the HVAC and cold asile and hot asile mechanism, then you will face the issue of power and cooling system, and your system is not going to work properly due to the temperature issues. Interconnected, so I already told you, because the work is distributed amongst the multiple node, and after performing the computations, node need to respond to the system. So this interconnection with the high speed network, like that InfiniBand is one of the very best example is given over here. It is a mechanism of transferring data in high speed network is important. Cluster management software, so we will use a tool that is called Slurm, OpenPBS. These are the various tools which are used for the cluster management. So in our lab, we are going to use this software that is called Slurm. So we are going to use it. I see that lot many questions. Mani Arora is asking, are the nodes and head load balancer logically created? It can act as a both type. You can create the logical software-based load balancer is also available, and hardware-based load balancer is also there. So you can create as per your requirement and budget how you are going to do, and as per your computation load also. No. So type of clusters, I already given you idea about grid. So you having the idea of heterogeneous, Beowulf. So these are very important because I segregated all these information from various sources. So one category of cluster is called Beowulf cluster. What we are going to use, we are going to use commodity hardware and open source software. That is the biggest thing. Means this cluster is always designed with the minimum cost. It is a cost effective solution, and it is going to provide you the optimized performance. It is not equivalent to the paid, means all the paid software, but it will provide you the good solution. If someone want to do some research, they can go for this particular cluster configuration, and they can see that what kind of idea is get generated, what kind of result is coming, how actually cluster works, how we can design the cluster. So if you are designing a cluster using commodity hardware, means the generic hardware which we are using. For example, in my organization, there is a lab of 50 PCs and nobody is using that lab. I can use that lab with the help of Beowulf cluster architecture as a lab which is going to perform HPC mechanism, which having the capacity of parallel processing. Second is grid computing. Grid computing connects geographically distributed resource into unified HPC environment. I already given you the idea. But in the case, if you are creating a cluster with the grid, so very good internet connection, very good connection is high-speed network connection is required. So grid-based HPC is always possible by very large organization. They having the lease line from one office to another office. They having dedicated mechanisms for transmitting the data. So small companies are not going to afford it. Small companies having the HPC with a centralized cluster only. Cloud-based cluster, I will give you the example. Heterogeneous clusters, you already aware about that, combine the different types of hardware. Grid is one of the example for the same. High performance virtual cluster. Sometimes we will not go with the physical configuration. We will use the virtualization if we having an entire massive infrastructure. And with the help of virtualization, we can create the cluster. So that is called high performance virtualization cluster. Hybrid clusters, it is going to combine the features of on-premise cloud cluster to the balanced performance. So that is the category of hybrid. I having the physical cluster also, and I deployed something over the cloud. So I will show you one or two examples how you can able to see that what are the cluster services are available on the clouds and how we can configure. There is a proper documentation and detailed videos are given by the cloud service provider. So if you are doing the research, you can able to do. Now, few questions I will take it. So Vandana Sharma is asking, is there minimum and maximum node? No, there is a no limit. It is dependent upon how many cluster, if you are designing any infrastructure, so you can able to handle that many number of devices. So there is a no limit of the same. Kubernetes version 3 points cluster, how do okay, when we're talking the Kubernetes is a completely different task. What we are doing when we are doing the migration, in the case of one node goes dead, we will migrate the entire task to the another node, Dr. Prashant. So we will coming on that particular thing, then we will discuss. In the Kubernetes also, it is dependent upon that how we are going to configure the cluster for which particular capacity task. So we can configure it. So I'm just going to show you a few things. Just give me 1 minute so I can share my screen once again. Entire screen is required. So just be with me. Okay. So if you want to check, you can go on AWS HPC. You can check it out. So there is a high performance computing on AWS. And if you will scroll it down, you will see that what are the benefit and what feature. For example, I am doing research in compute where the massive computation is required. You can go and check that how we can configure Amazon EC2 for high performance computing environment. You can see that it is going to tell you about the same. Or if you will see that one option, that AWS HPC cluster. So multiple will come, you can check it out. So parallel computing services are there. Now, one thing which I research and engineering studio on AWS. So there is a pre-configured high computation servers are there. What is required? Cloud9 service is required. If you are working a research, if you are doing research, you can use Cloud9 AWS. You can check it out. So this particular service is used for writing, you can say that code which is fit for the HPC environment. So you can integrate this particular environment. I will show you that video also. On video, there's Cloud9. Yes. You can read this document which help you out. Simplify HPC cluster using AWS Cloud9 and AWS Parallel cluster. So this is going to provide you the very good explanation, and you will get many examples over here. So this is a good solution. AWS having lot of resources for the same. So you can utilize. I am going to paste this link for everyone. Can check this out. Yes, so it is a detailed document is available, so you can search. And if you go on that on the YouTube also, or the official web page of the same, so you can see the videos also. They have given the configuration videos, and with the help of these videos, you can configure as per the requirement. Means if you want to configure and do some research, you can configure your HPC computation mechanism. And if you use AWS Educate account, you can able to make free. You will able to get the free resources. But in that case, the Educate account is required. So we already covered this, that scalability and fault tolerance due to the multiple nodes are available in the cluster. So if one or two node goes down, then also we can able to provide the service. So scalability is one of the major and prominent feature. So one is scalability. Now, after scalability, we will see that horizontal scaling or vertical scaling. So when we're talking about the horizontal scaling, we are talking adding more nodes in runtime. For example, if I have a cluster with 3 devices, and in a runtime, if it is required, I can able to add one new device, what we called horizontal. Second is vertical scaling, means I have 4 devices in my cluster and I can add additional RAM. Additional RAM I can add more computation power, more CPUs. So it will comes under vertical scaling. Where we are upgrading the indivisible node, it comes under the vertical. Where we are adding something or removing something in from the cluster, it will comes under the horizontal scaling. Scaling, adding comes under scaling, when sometime we will descale also. Fault tolerance mechanism, already you are aware, if one system goes down, another can able to handle the request. Checkpoint restart features. So it allows the computational task to save the progress periodically. So there are multiple features like that. You can relate with the snapshot. So in the clusters, we having the checkpoints. With the help of snapshot, what we can do, we can able to create the point in time copy of the data. Similarly, with the checkpoint also, if we want to something, we can take the point in time copy over here. Real world applications, you already discussed that, financial, geographical, and number of things. So what are the type of nodes in the cluster? One is head node, we already discussed. It is a central management point handling job scheduling, resource allocation, and system monitoring. Second is compute node, which is going to perform the actual computation task. Login node, this is very important. Sometime this node is the part of head node only. Sometime we having a login, separate login node that will provide an interface to the user to connect the cluster, submit their job, and manage the file. So you can see that there is a login is also one of the important one. Storage nodes is also there. So these nodes are specially responsible for. So how we can configure a storage node? I already given you the example with the help of NFS, with the help of NAS. NAS stands for network attached storage, or with the help of parallel file system. So this parallel file system help us to distributing the files in the parallel devices. Service nodes. So you can going to provide additional functionalities such as services, database, software specific tasks. So these nodes are not the mandatory part. If you are configuring the cluster, HPC cluster with specific features, and if you want that few nodes are going to handle a specific kind of service, so you can include these kind of service nodes. Any confusion with respect to same, please let me know. Okay. So when we are configuring the node, we will see the practical also of this. What is required? The processor specification is required. Memory capacity is required. So when we are storage options are required. Network interfaces are important part. Power efficiency is important part, and custom configuration is important part. So when we're talking about the processor specification, so compute nodes often use multi-core. Like that, we will say, na, in my laptop is Core i7, Core i9. And similarly, if you want some nodes for the cluster you required, what about the barriers of entry for HPC on cloud? Dr. Prashant, one thing is the grid-based mechanism. After completing this module, I will come to your question, then we will discuss in detail that what are the barriers and all those things. So processor are there. We need to take a good processor if we want that node, and it is completely dependent upon the type of task you are going to do. The commodity hardware processor is also work if we are working on the basic task. If we are just designing, sorry, memory capacity. So we will not go with the 8 GB, 10 GB or 12 GB. If you are defining the cluster, you always need to go for the GB RAM, 128 GB to several terabyte, depending upon the everything. When you are defining the cluster architecture, everything is dependent upon the requirement. That what is your requirement? Storage options. So you having the multiple storage option, you can go for the SSD based storage option. And in SSD also multiple type of SSDs are coming. And as per your budget and requirement, that how much input output per second, what is IOPS you are looking. So for storage option, what is very important thing? IOPS, input output operations per second. Now, network interfaces. So how much bandwidth is required? We always go for the maximum low latency, because in cluster, low latency networks are required. Power efficient. So nodes are designed in such a manner they will maximize the energy efficiency without compromising the performance, because HPC is majorly focused on the performance. So when we are talking about the HPC, we cannot design something which is compromised with the performance. Custom configuration. So some nodes are tailored for the specific workloads such as AI ML. So I already told you that you can design that some kind of nodes, some nodes are only going to handle a specific kind of task. So go through this real world examples of compute nodes in HPC system. So one is IBM Summit. What is going to utilize Power 9 CPUs and NVIDIA GPUs and delivering peta-scale performance for scientific research. So if someone asks you, give some real life example of HPC system, so you can say that IBM Summit is one example. Supercomputer with the ARM processor, which is working, and it is designed for the application like COVID-19 research and disaster predictions. So this is also one of the Google TPU pods, Cry-XE series. These are the various kind of HPC systems which are utilized for various purpose, whatever the purpose you have seen. For scientific research, IBM Summit is one of the solution, and n number of other is available. You can do the research. If someone asks, okay, tell me one example which is used for the medical research and medical collaboration, you can give this system which is used for the COVID-19 research and disaster prediction. If someone for machine learning and artificial intelligence task, Google TPU pods are one of the example. If weather forecasting or climate modeling, Cry-XE series is one of the example. Now, importance of networking in HPC. So why it is very important when you are configuring networking is very important when you are configuring HC. First is high speed data transfer. High speed data transfer is required. Scalability support is required. So advanced networking facilitates the seamless scaling of cluster. So if we are adding some more node and my network is not designed in such a manner that that network is capable of handling more load, so we cannot able to perform scalability. So always network need to design in such a manner that it is ready to handle the load or traffic if we are increasing the devices. Means if you are increasing more devices, more traffic is going to generate. Low latency communication. Always go with the criteria and design such a manner. You need to do the bandwidth planning in such a manner that there is a minimum latency and proper real-time synchronization is possible. Data sharing. Enable the shared access to the database, making it easier to collaborate across the node and storage system. If we have divided, okay, this is my storage server and all the nodes are putting their data on the storage server. So what we required the data sharing mechanism and fast processing of managing that particular data. Load balancing, all of you are aware about, and enhanced fault tolerance. When you design your network architecture, you need to take the steps for preventing the failovers. If one device fails, then how you are going to recover from that failure and able to provide the service. So we will do the planning as per the HPC use. So when HPC is used for any critical task, what we will do? We will design a multiple fault tolerant network with redundant resources. So if one resource goes down, the load is switched to the another resource. It is not when we are using HPC for critical tasks, we will not dependent upon the single system. So we need to design in such a manner so we can maintain the fault tolerance over there. So we already covered this type of storage. So there are different kind of storage is used. One is shared storage. Another one is distributed storage. Another one is parallel file system and use cases. What are the use cases of different kind of storage? So if we talk about the shared storage is having the lesser cost if the storage is shared. If we will go with the distributed storage, so distributed storage means data is distributed among multiple storage drives. Shared storage because one storage drive is configured in one single place and all the systems are going to put the data. So these are the various type of storage which is used in the HPC scenarios. So these are the various network topologies and interconnections are used. So go through these various topologies and interconnections. Just take 1 minute short break, analyze it, and then we are going to start from practical configuration. If we need to design our own cluster, HPC cluster in our local system, how we can able to design just for understanding. And similarly, whatever the steps I am going to tell you in this particular FDP, if you apply the same steps, you can able to design in your labs also. So if in your labs you want to design the system, you can follow the same steps and you can able to design in your labs. So be with me, take 1 minute to analyze this slide. Then we are coming with the mechanism of designing the same cluster mechanism. So take 1 or 2 minutes to analyze. Yes, sir, you can punch 1 or 2 practice questions so they can proceed with the practice questions till the time.
I'm punching one practice question to you. Here it goes, guys. Just check out. There's one question for everyone. Attendance already we have punched. There is one question. Please.
Okay. So shall we proceed? Just give me the consent so we can proceed from that point. Thank you. So first we will see the challenges little bit. Then we are till the point whatever we discussed. If anyone having any question, he or she feel free to discuss that question. Anyone having any doubt or question till this point?
Sir, we have punched one question. People are attempting. So
Okay,
let us see.
no
Let us
issues.
give them 1 more minute.
Okay, no issues, sir.
We have punched it on HPT system cluster architecture. I've got 39 responses. Half responses have come. Let us hope others are also doing it. Please do it.
Ajay sir, shall we proceed?
Yes, sir.
Okay. So now we need to understand what are the various challenges in HPC networking and storage. First is latency sensitivity. So due to the latency sensitivity, it is very much important to ensure the quality of service in the case of networks. If you cannot able to design a robust network which is least in the latency, so you cannot able to perform multiple tasks properly. So latency is very important. Bandwidth bottlenecks is also one of the important challenge, because insufficient bandwidth can limit the scalability and efficiency of the cluster. Why? Suppose that in my cluster initially I have only 6 systems. So what I did, I think that okay, maximum bandwidth required by 6 system is XYZ. Maximum bandwidth is required. Now what we are looking for, we are looking for add 3 more system, but the the network architecture is designed with respect to 6 systems only. So whenever I will add 3 more systems, it is going to create the situation of bandwidth bottleneck. Data management complexity is also there because handling the vast amount of data across the distributed and parallel storage system is a challenge. Energy efficiency, it's always remain in the computation. Energy efficiency is always remain a challenge. Hardware cost. So when we are setting up HPC, the hardware is too costly. It is not easy for the smaller ecosystem or smaller organizations to set up this kind of HPC architecture. Fault management, ensuring the data integrity, unencrypted communication during the failure requires a robust solution. And so the fault tolerance is also one of the very important phenomena which we need to take care how we are going to manage, because it is a massive computation and number of nodes are available in every cluster. On which particular node, what issue arises, what we lacked. So identification and management. That's why we are more dependent upon the software-based management solution to easily identify and fluctuate and highlight those points. So see the one diagram which help you to understand the difference between CPUs and GPUs. This is the specific slide which I love. I created to give you the idea. So CPU for the general purpose. CPU is ideal for the sequential task, managing multiple processes and handling the diverse workload. But CPUs are more suitable for handling the, you can say that, serial or sequential task when it will come. When we're talking about the GPUs are mostly designed for the parallel processing. So they are designed for handling thousands of tasks simultaneously, making them suitable for AI, ML, and for anything where the massive computation and parallel execution is required. Architectural difference, if you want to see, CPU has fewer core, which is optimized for high clock speed, while GPUs have more cores, thousands of smaller cores, and that is optimized for the parallelism, executing multiple tasks parallelly. Use case of CPU, so best suited for serial processing tasks, complex algorithm, and HPC node management. If we will talk about the use case of GPU used for image rendering, deep learning, molecular solution, and data visualization, where we require a lot of parallel nodes and tasks need to be executed, then GPU is much preferable as compared to CPU. So in clusters, we will follow the combined uses, hybrid uses, because designing entire systems with the GPU is not a solution. Combined uses. So modern HPC system integrates CPUs and GPUs for hybrid performance. In the laptops also, you can see that for several tasks, you can switch yourself on graphical processing unit also. All the gaming laptop will come with that computation facility and that feature that you can switch whenever you want. So this is very important slide. Means it will give you the basic idea about that what is the major difference with respect to HPC. So exploring HPC cluster. So we already discussed about the cluster component. Then after cluster component, we are going to access the cluster. Then we are going for job scheduling workflow. Then we are going for exploration tools. So these things are important when we are finding. So exploring, we will see practically how we can design and define this kind of cluster mechanism and in upcoming slides. So now I am going to tell you how to configure this cluster. So just give me 1 minute. I will let you know. New slide. Okay, what I am going to do, how we are going to demonstrate. So for demonstration of entire cluster setup in local system, what we are going to utilize? We are going to utilize following system configuration. I am going to take Ubuntu machines for implementing this cluster. So this is first machine and it is acting as a master node. It is acting as a master node. In this master node, what softwares we need to configure? So I am going to design a HPC cluster with 3 slave nodes and 1 master node. So this is a master node. Then I am going to configure slave node 1, slave node 2, and slave node 3. This is slave node 1. This is slave node 2. This is slave node 3. So step 1, on master node, because I want to manage all the system from master node. So for managing all the system from master node, I am going to install here SSH. So the first command which I am going to run, I am going to write apt, because I am using Ubuntu. So install open-ssh server. Done. After installing this SSH server, we need to install SSH client on all the systems. So we need to install SSH client. We need to install SSH client. We need to install SSH client. Now, master node can anytime perform login into these slave nodes. Master node can anytime perform login into these slave nodes. Second thing, if you want to make the passwordless login, so for passwordless login, what we need to do, we need to configure SSH passwordless login using SSH keygen. So once you generated the keys, then what you need to do, you need to copy public key on slave node 1, on slave node 2, on slave node 3. So once you copy the SSH public key on slave node 1, slave node 2, and slave node 3, you can easily able to log in into slave node 1 and slave node 2 and slave node 3 without any password, because what we did, we configured into the keyless mechanism. We are not going to utilize anything else, as we are going to utilize the keyless, because every time again and again as a master I need to log in into the slave node. So I am going to follow this exercise. Now fourth point, when I am configuring this, in the fourth step, what I need to do, if you want to make a very human-friendly name, you know that in your cluster only 10 systems, so you can go and edit host file. What you are going to do, you are go and edit the host file of master system, of master node. So what command you will write? You will write nano/etc/host. Once host. Now, what you need to do, for example, this system IP address is 10.0.0.5. This system IP address is 10.0.0.6. And this system IP address is 0.0.7. Now, this is node 1, this is node 2, and this is node 3. So in this file, you can create the 3 entries that you can say that 10.0.0.5 is equal to N1, 10.0.0.6 is equal to N2, 10.0.0.7 is equal to N3. So instead of giving entire IP address, now only give the node name. It is very easy. Why I am telling you? Because when we will create a grid architecture or a cluster architecture, we need to make the things very easier so we can make all the arrangement and documentation properly. So after configuring these things, now all the master slave communication is done. Now step 5, I am going to take the help of network file system for implementing a storage cluster. Storage cluster means this master node is for, suppose that if we are having 100 GB, here also having 100 GB capacity, here also having 100 GB capacity. So total storage is 300 GB. Single system is capable of storing how many GB? Single system is capable of storing 100 GB. But if any user will come and he want to store the data of 200 GB, with the help of this NFS configuration, we can able to store the data of 200 GB. Which particular software is going to manage this storage? NFS is going to manage this. Now, what we will do, for the NFS configuration, the complete architecture diagram is divided into two parts. On master server, we know on master node, we need to configure NFS server. What we need to configure? NFS server. And on the slave nodes, we need to configure NFS client. For configuring the NFS server, we need to use two files. One file is called /etc/exports /etc/export, and one we are going to create master directories, master directories. So user is going to interact with the master directory. Whatever the user will store is stored in the master directory, and everything will get distributed. User is not aware about that his data is stored on N1, or his data is stored on N2, or his data is stored on N3. User is only aware about that he is stored data on this particular system. So this is a complete basic architecture diagram which we are going to implement. Right now, till this point, if anyone having any question, one by one you can ask, then we are going to proceed further from this point. Everyone is clear with this diagram architecture, how we are going to set up everything? Thanks, Dr. Bishan, for your reply. Okay. Okay. So now we are coming on the scenario where we are going to configure the things. Because entire configuration is not possible, but I will guide you that what are the things are required for entire configuration. Shall I delete this, or can we use low configuration system commentary as a slave node? Yes, you can use. I am going to use the low configuration system, and I am going to use entire open source solution. So if you want something related to storage, you can do. If you want something related to the computation, you can also utilize like that. I required a computation power of 10 systems, so we can create a HPC cluster with commodity hardware, and we can do. This is the entire configuration like this. So like this, I am doing for the storage. You can do it for the virtualization and all those things. Sir, we use Ethernet ports and switch. Yes, Nikhil, we required Ethernet switches as at that particular point of time. And what kind of computation is required? Like that, I required a good bandwidth, so you can use gigabyte Ethernet ports. If you required a minimum bandwidth, you can use fast Ethernet. So it is dependent upon what kind of requirement you have. Sir, client node is fault tolerance implemented, the duplicating the task or the host node, which one is originally preferred? Okay, in the case of, you can say that the client node, the fault tolerance is like that. Initially, there are the 4 nodes. So here we are not going for a hot standby. For router and networking configuration, you can go for the standby routing protocol like that VHSRP and HSRP. But here we are not going for that. One node goes down to another is going to up in default architecture. But you can customize this architecture with the help of code in the system balancing like that. I configured my entire network that always 10 system must be running, and I run the script over there. If one system goes, suppose that 10 is running simultaneously, one goes down, There is a master system who will take care of it, and one script is executed in the background, and one more system is going to be up. So we need to define that particular thing accordingly. Any other question to anyone, please let me know. So just I will show you, I am going to erase this, what infrastructure is required for setting this same. So you can come prepare for the next class. So in that next class, we will do the demonstration proper. So you can see that in my system right now, I just configured one server and one node. My virtual machines are visible to everyone. So initially I configured server with little bit higher configuration. I have configured with 2.8 GB RAM. I used 8 processors, 8 core of the processor. Now I am going to virtualize. This is the virtualize. So I am going to switch it on. And similarly for demonstration, because you having the VMware, create 2 more nodes. So node 1 I have already created. One more node I will replicate in front of you. So we will use 2 nodes for that particular process. So first I want to do all the configuration over the server. So server is getting up and getting ready. So we will wait for 1 or 2 minutes. Once the server will get up, so I will try to execute few commands on the server, which is required for the same. You can use Debian and Red Hat, whatever the systems you want. I am going to use Debian over here. So the Debian system is going to be utilized over here. Till the time it is getting up, you can ask the questions. If you have any questions.
You can ask the questions or we will ask. Raise your questions.
Okay, all good, I think so. So we are setting all these things. So for tomorrow's class, what I expect from you means all the learners, please come with the pre-configuration. Can we perform on VirtualBox? It is open source. Yes, you can use. Right now, VMware Workstation is also free. Money you can use VMware. So we can create the cluster in VMware for learning purpose. Yes, Nikhil, you can create the cluster in VMware for the learning purpose. I am going to explain the same thing in the next lecture. That means in tomorrow I have a session, then I will help you out to setting up entire thing in the virtual environment only. But you required a machine with good configuration. I am trying to configure all these machines because in my laptop having 16 GB RAM. Sir, our own lab notes in Windows OS. Please tell how to set up HPC. Yes, you can go with the Windows OS also. You can set up the HPC. I will tell you, not an issue. So right now I am going to log in into the server. The first thing, you need to install the SSH server. Then you need to install the NFS server. 2 servers are important for this configuration. So go on the terminal. So first command which you need to perform, sudo apt sorry. So we are going to install the SSH. The step 1 is this. Once you will install the SSH, then what you need to install? You need to install the server. So once after installing the SSH, 2-3 more commands, so I will show you the history. You need to start it. So for example, if I want to check that what is the status of SSH command, so I am going to write systemctl status of SSH. So what is, you can see it is inactive. For enabling it, what you need to write systemctl start SSH. So what is asking? Authentication. So I have given the authentication. Now check the status. It is active, but if you reboot the system, it is not remain active. So I want to add every time whenever my system reboots, SSH will get restarted or started. So what I will write, I will issue the command systemctl enable SSH. Again, give the admin privileges. Just wait for a minute. Systemctl enable SSH. Now done. Come on the normal user mode and you will check. So you can check services enable and first preset. So when you will reboot the first these three commands, you can come and you can check that whatever the commands I executed. So you need to follow these commands for setting up your system. Don't forget the first one. 2nd to 9th command is useful for you guys. Okay. Now, after this, what you need to write? You need to install the NFS. So you need to write sudo apt. Before this, you can use a command ssh use keygen. So it is asking that, okay, what key pair are going to generate? Because I told you, you need to copy the key. So again, I generated. So how we can verify that key pair is generated? Go into the cd.ssh, do ls-l. You can able to see there are the public keys there. This is private key. If you do normal ls also, you can see. So what I am going to do, I am going to put this public key on all the systems. So right now I have only one system. So you can see that SSH part is done on the server. Now copy part is remaining, but copy part we will perform once we have all the servers are active, all the slave nodes are active. Right now, master node I am configuring. So second software which is required on the master node is we need to install the NFS server. So which is going to provide us the seamless management of network-based storage. So I am going to write sudo apt install NFS-utils is the package name. Wait. NFS-utils. Package name may be little bit updated. NFS- yes. So we can check it out. So you can, NFS-utils is the package name in the case of Red Hat. If you are using CentOS or Red Hat based system, then you need to use. In the case of Ubuntu, what command we need to give? Apt and install NFS-server. So if you execute this command, what we will do? We have configured the setup of NFS also. So all the system, all the configuration on master node done. So I am just going to show you the history of the command so you can get the idea. This, don't configure this one. Consider the 18th one and all the top command. So see, once whatever we perform today, try to come with the pre-configured system. So it will not take more time for me for explaining and showing you the demonstration related to the same. Till this point, if anyone having any question or doubt, you can ask because we are going to wind up today's session over here. See you tomorrow.
asking one more question to them on poll.
Yes.
I'm giving them one question to them.
Okay, sure, sir.
Can I?
Yes, sir. Yes, sir. Sure.
If you allow me, I can give two, but I have too many questions, but I'll give you one more question to them.
Sure, sir. You can give as many questions you want.
And it is an overview of computer nodes. One question. Let us. It has gone. The link is there. Let me give one more. It is on storage. That's it. There are two questions. I request again. Please do it. There are two questions, 2 minutes.
Okay, this sir, can we leave now or I need to stay for some more time?
If there is any question, then it's okay. Otherwise, have a nice time and good demonstration as usual by you.
Thank you
So
so much, sir.
we will be meeting tomorrow again
Sure, sure, sure. Thank
at
you so much.
a scheduled time. And if someone has any question, not getting video icons, you will get videos Sir, you are going to be sure this video is going to be downloaded and then sent to you on your mails. Definitely. There is no issue. So you feedback link also. You will get tomorrow in your mails the feedback link. In the meantime, you can give your feedback, informal feedback on the chat. On the chat, you can give or you can speak. Navjot Kaur ma'am wants to speak. You can speak, ma'am. And we will see you tomorrow, everyone.
I believe he left. It was a great session, definitely, sir. And it'll be good to have the hands-on in
Tomorrow.
the sessions. So
Right.
I'll add on to our knowledge. Right, sir.
Great, great.
Right, sir.
Thank you. So we'll be sending you the videos as well as the feedback links of the sessions tomorrow. So please do fill the feedback links and give us a chance to improve. We are going to close the question links right now after leaving the meeting. So if you want to do questions, you can do. Participants have left. Neha Sharma, you are the host now. Now you can do the rest of the formalities.